Hello everyone. Today we are learning the subject of electromagnetics, and we in the last session we have studied about the few numericals related on the electromagnetic radiations. So still today also we will continue the numerical on the basis of your electromagnetic radiations. So we will start with a few numericals. Keep ready your pen, notebook, and the calculator. We may cross verify your the answers. So note on this one, a magnetic field strength of 5 macro ampere per meter, 5 macro ampere per meter is required at a point on theta is equals to pi by 2, comma 2 kilometer away from an antenna in a free space. Stop neglecting the ohmic laws. How much power must the antenna transmit if it is A part is given? Hertzian's dipole of a length lambda by 25, the half wave dipole, and the C part is nothing but quarter wave monopole. So these are the various types of the antenna available, and accordingly we are interested to measure the radiation from the each and every you can say the dipole which is changing. Okay, so here what they are asking to calculate, few parameters are mentioned, that is nothing but your the magnetic field strength, that is nothing but your the H is given, your theta is given, your what you can say the wavelength is also given. Okay, and wavelength in terms of the differential length that is given. So you need to calculate in all the cases if the dipoles are changing, if the various kinds of dipoles are used at that time, how much power must the antenna transmit. That we are interested at the transmitting antenna, and we are going to calculate the radiation of that. Okay, and by observing all these parameters which is given, and we need to find out the unknown parameter, that is nothing but how much power is transmitted, okay, through the transmitting antenna. So how we can start, the A part is for the Hudson dipole. So that is given, the dl is equals to lambda by 25. The magnitude of the magnetic field is given, which is already given at the beginning of the question, that is nothing but 5 micro ampere per meter. So we can understand here the theta is given, we can understand if the theta is there, so the possibility of your the either the cylindrical or spherical coordinate system. So you can take here or you can say the spherical, just looking at the shape of the transmitting antenna in the dipole form. So here the magnitude of that magnetic field is nothing but the what we can say, you can take the r theta 5. So at the time, why we are taking this mod, just because of your the magnitude. Okay, so mod of this H5 is equals to I. This is the derived expression. So don't get confused to how you got all these things. This is in the derivation part only. So while you are going to simplify, at that time you should remember what is the electric field intensity, what is the magnetic field intensity, and in which direction we are going to find out. So here we are, as the theta term is given, we are interested in the phi term. So Im dl sine theta divided by 2 pi r. So lambda by r, 2 lambda by 2 lambda into r. R is the radius, theta is the angle. Okay, and the lambda is nothing but your the wavelength. So what are the given here, the parameters, the H is given, that is nothing but you are the 5 micro, 5 to 10 to the power minus 6. So Im, you need to calculate the Im. Okay, because the Im is unknown. Dl is given, that is a lambda by 25. Okay, theta is also given, that is a pi by 2. So even the lambda, that is nothing but 2 kilometers, so 2 into 10 to the power 3. So which is unknown, only the Im is unknown. Dl is mentioned, theta is mentioned, lambda is mentioned. Okay, so what you can say, the 2 lambda means a radius is mentioned, that is nothing but the 2 kilometers. So that r is mentioned. Okay, r is mentioned. So how we can get this one? So above lambda and below, numerator and the denominator, that will be cancelled out, and you will get the unknown parameter, that is nothing but your the peak value of your the current, that is nothing but 0.5 ampere. So for the further case, we need to get the answer of your the IRMS. So IRMS will be equals to your the effective current, that is nothing but the I effective, and that we can calculate Im by root 2. So Im already we have calculated 0.5 and root 2. So in this way you can get the IRMS value. So 0.3535 ampere will be your the IRMS. Similarly, if you are going for preferring for the Hudson's dipole for the radiated power, so P radiated is equals to 80 pi square dl by lambda of bracket of whole square into I effective whole square. So these are the derived expressions. So in this way we can calculate the radiated power 80 pi. So dl is given in the numerical lambda by 25. This lambda will be as it is. This is the squaring. How we have calculated the I effective, just because of the I with the help of this Im. Okay, so Im and root 2. And how we got that Im? In the previous slide we have seen how we have calculated the peak value of your the current. So in this way you can substitute the value of your the DL, the effective current, and you can calculate the radiated power, that is nothing but 157.8 milliwatt. 157.86 milliwatt if you do with the calcium. Now go for the by changing the dipole, you can again find the radiated power. Okay, here what we are using for the half wave dipole, in the previous case that is a Hudson's dipole. So the on the that expression was on the basis of your the view of the scientist. Okay, so here also the second dipole is nothing but the half wave dipole. In that the dl will be your the lambda by 2. Okay, and the magnitude you can find in the field of the magnetic field. So that is a mod of H5 is equals to Im divided by 2 pi r, that is a radius in bracket cos of pi by 2 into cos theta divided by sin theta. So if you observe this expression, which is derived expression for the half wave dipole, so here the what we can say again, the Im you need to calculate what are the parameters is given, that is H5 is given, the theta is given, and the r value is given, radius. So in this way substitute the value of H5, substitute the value of r, substitute the value of the theta. So you will get the only the unknown parameter will be your only the Im. And if you are going to substitute all the values of your the theta, r, and the phi, you will get the Im will be 20 pi milliampere. If you want to substitute the pi value, then also you can get that is a 3.14. So you can get the exact value of your the peak current, that is nothing but the Im. Okay, in the milliampere, that is also possible. Okay, so see here for the next part is nothing but to calculate the power radiated by the half wave dipole. So P radiated is equals to, the formula will be for the half wave radiated power can be calculate I square R formula, I square R. So I will be here the IRMS square into the radiated resistance. Okay, so what is IRMS will be the Im by root 2 of whole square into RR. So here radiated for the half wave, radiated resistance for the half wave is nothing but the 73, which is not given, but it will be always be 73, which is derived in the expressions of your the theoretical parts. So here the radiated power, if you are going to substitute the value, so you will get as, so if you are going to substitute this one, if you are going to the Im, which you have calculated 20 pi milliampere, so you can substitute this value of a bracket of whole square into the 73, you will get the radiated power 144.09 milliwatt, 144.09 milliwatt. Substitute the value of IRMS with the help of the Im. We have calculated in the previous case. The radiated power, radiated resistance is nothing but the 73, just because of the half wave type. Now come towards the C part, which is given because we need to change every time the dipole, and we need to calculate the peak current. We need to calculate the what we can say the radiated power in all form of your the dipoles. So the third case is mentioned, if you have the quarter wave monopole dipole, at the time you can take you can consider or the take the differential length, that is nothing but you are the lambda by 4. So see here in the first case lambda by 25. So in the second case, that is a what you can say the lambda by 2 you have taken, and in the third case you have taken as your the lambda by 4 for the quarter wavelength. Okay, so the maximum current for, or the peak current or the maximum current for the quarter mono dipole, you can calculate which is the similar to your the half wave dipole of your the previous case, that is nothing but the 25 milliampere. How you can find the radiated power? With the help of the same formula, that is nothing but IRMS square into the radiated resistance. Okay, if you are going to substitute this value, Okay, you will be able to find only the changes in the radiated resistance. That will be your the 73 will be divided 73 divided by 2. So here will be your the 36.5 ohm will be your radiated resistance in the quarter wave monopole. Okay, so in this way you can calculate the radiated power, which is equals to your the Im divided by root 2 of bracket of whole square into R radiated. So 20 pi, that is a milliampere. So 20 pi into 10 raised to power minus 3 divided by root 2 of a bracket of whole square into the 36.5. You will get as the radiated power 72.045 milliwatt. 72.045 milliwatt. So go for the next one. An electric field strength 10 microvolt per meter is to be measured at an observation point theta is equals to pi by 2 with a 500 kilometer from the half wave dipole antenna operating in air at 50 megahertz. The A part is what is the length of the dipole. The B part is the calculate the current that must be fed to the antenna. The C part is find the average power radiated by the antenna. So in this case, the electric field strength is given, if the frequency is given, the theta is given. Okay, so and you need to find out the three parameters, that is nothing but the length of the dipole. You need to calculate the current with that particular antenna, and you need to find out the average radiated power of antenna. So how we can start here with the help of the A part, that is nothing but the wavelength can be calculated. Lambda is equals to, that is the velocity of light, V by F or C by F. So here lambda will be 3 into 10 raised to power 8 divided by F is given 50 megahertz. So in this way you can get the wavelength is nothing but 6 meter. Okay, 6 meter. If you are going to substitute the value of the C and the F, okay, and you can calculate the wavelength. So once you got the wavelength, you can find the further parameter, that is the half wave dipole. You can find the length of the half wave dipole. The length of the half wave dipole can be calculated as capital L is indicated the length of the half wave dipole, or simply length of the dipole. So L will be equals to lambda by 2. Okay, just because of the half wave dipole, so lambda by 2. And what is that lambda is 6. So in this way you will get the length is nothing but 3 meters. Length you will get as a 3 meters. Now go for the second, that is nothing but the magnitude of the electric field is given by. So electric field magnitude already given, that is the 10 what we can say milliampere per meter. So 10 into 10 raised to the power micro, 10 into 10 raised to the power minus 6. Okay, what is the expression, derived expression for getting that half wave dipole in the electric field intensity? That is nothing but 60 Im by R cos of pi by 2 of cos theta divided by sin theta. So here again, what you need to calculate the unknown parameter Im. R is given as your the what we can say 500 kilometer. 500 kilometer is given in the numerical. So 500 into 10 raised to the power 3, 60 into Im will be as it is. Cos of theta will be given as a pi by 2 is already given in the numerical pi by 2. Pi by 2 theta everywhere. Wherever you are having the theta here, you need to substitute the value of pi by 2. So likewise, the unknown parameter of Im you can calculate. The R is nothing but the 500 kilo. You can substitute the value of E theta. So the unknown parameter, that is nothing but the peak value of the current, you will get as 83.33 ampere milliampere. 83.33 milliampere you will get for the half wave dipole. Now go for the C part, that is for the again the half wave dipole. Already we are aware that is the radiated resistance is a 73 ohm. So in this way, by considering this value of your the radiated resistance, we can find the average power radiated by the antenna is given by. So with the help of the basic formula, that is nothing but I square R. The P average can be calculated as I square R, that is IRMS square into R radiated. Okay, so here you can find this, what we can say, if you are taking the IRMS square, so at the time IM square, this is 1 by 2 of R radiated into IM square. So already we have calculated the IM, okay, that is 83.33 milli. So you can substitute this one, so you can substitute the radiated resistance. Okay, so in this way you can get as the radiated power 253.47 milliwatt. 253.47 milliwatt. You will get this answer by so substituting the value of radiated power and other value, and with the help of the basic formula of your the radiated power, you can calculate the value. P average. Go for the next one. The radiation efficiency of a certain antenna is 95%. The radiation efficiency of a certain antenna is 95%. The maximum radiation intensity is 0.5 watt. Maximum radiation intensity is given as a zero point 0.5. Okay, and the calculate the directivity of an antenna. Calculate the directivity of an antenna. So here the P input is given, that is a power input and radiated power input power, as well as the radiated power. Zero point 0.4 watt and 0.3 watt is given. Okay, and what is given, that is a efficiency is given, that is a 95%, that is nothing but 0.95. And also given as a radiated maximum intensity, U max is given as a 0.5 watt. Okay, 0.5 watt. So here the A part you can calculate as radiation efficiency of an antenna is given by efficiency is equals to P radiated divided by P input. So P radiated we need to calculate, and the efficiency is given 0.95. The input power is given as a 0.4. So in this way you can calculate the P radiated 0.38 watt. 0.38 watt. So the directivity of an antenna in terms of the radiated what we can say radiation intensity can be calculated as D, that is nothing but the directivity. Okay, directivity of the antenna in terms of the radiation can be calculated D, that is equals to U max divided by P radiated divided by 4 pi. So this value are already given in the numerical 0.5. This we have calculated 0.38, we have just now calculated in the previous slide, and the 4 pi. So if you are going to substitute this value, you will get the directivity will be 16.5346. 16.5346 is nothing but your the directivity. So directivity of the antenna. Okay, so here the two times, that is with respect to your the input power as well as with respect to your the radiated power. So two times we are going to calculating this value. Once with the help of the here should be P input. So in this way just there will be the change. Okay, there will, what is the change here? That is nothing but the 0.4 and the 0.5. Likewise that minor changes is there. With the help of that you can calculate the directivity. Go for the next one, that is nothing but a lossless half wave dipole antenna of the rectangular form is given 73 plus j of 42.5 ohm, having the directional gain of 2.15 dB, is driven from the 10 volt to the 50 ohm generator. Determine the electric field intensity at a distance of 10 kilometers in the plane perpendicular to the antenna. So equivalent circuitry is given here. If you observe this equivalent circuitry, you will be able to find that the resistance value of your the half wave dipole 73 plus J of 42.5 ohm is given. The current will flow and the resistance value is 50 ohm and the 10 volt is given. So how we can go for the finding the currents and the radiated power? The current can be calculated by observing that equivalent circuitry is nothing but I is equals to V by R. So with the help of the Ohm's law, I is equals to V by R. So V will be the 10 and divided by R. R is the combination of two things. One is in the rectangular form. You may treat as a load also, and one is nothing but the internal resistance. So internal resistance value is the 50 and the load side is nothing but 73 plus J of 42.5. Now the magnitude will add, that is a 50 plus 73 will add. So 123 plus J of 42.5. This rectangular form will be converted into the polar form. So you will get as, okay, so 130.1355 angle of 19.06. If you are going to converting this one rectangular form into the polar, you will be able to find 130.133 angle 119.06. Okay, and this here the numerator will be the 10. So 10 divided by 130, and again the here angle is nothing means 0. So 0 minus of 19.06. So you will get minus 19.06. 10 divided by this one is 0.0768, and angle of theta 1 minus theta 2 is nothing but minus 19.06. Okay, degree ampere. So we are interested in the magnitude maximum value. So that is nothing but 0.076 ampere is nothing but peak value of the current or the maximum value of your current. How we can find the power radiated? That is nothing but P radiated is equals to P radiated in terms of the IRMS is equals to I square IRMS square dot R radiated. But if you want to convert into the maximum current, 1 by 2 of R radiated into the IM square. So what is the IM? Already you have the value of IM 0.0768. You can substitute. What is the R radiated? That is nothing but the 73. If you are going to substitute the two values, that R radiated as well as the IM, so you will get as the final value of your the radiated power. That is nothing but 1 by 273 and 0.076 of whole square, 215.28 milliwatt. 215.28 milliwatt. Now, again the question is arises, we need to find out the further part, that is nothing but the derivative or the directional gain. Derivative as well as the directional gain in terms of the, what we can say, the derivative gain. If the gain is given 2.15 in terms of the dB, okay, in terms of the dB. So just substitute, we know very well the derivative gain can be measured in terms of the dB. So here the, what we can say, we are taking in terms of the theta and the phi, in terms of, in short, theta phi, or you can say the dB. So that is 10 log 10 of given value, 10 log 10 of given value. If you want to do the anti-log, okay, so anti-log of that given value divided by that, this 10 will come down, this 10 will come down, and this will become as an anti-log 10, anti-log 10. So likewise, what is the given the anti-log 10 if you are doing? So this is with the dB and this is without dB. So 2.15 in terms of the dB divided by the 10, that is you need to take into the anti-log. With the help of the calculators, you will get 1.6405. 1.6405. Okay, so as the question in the question is mentioned, we need to find out the electric field intensity. So that's why we are doing all these things to calculate the directivity gain, as the few parameters are given in terms of the directive. So the directional gain is given by GD is nothing but the directive gain or directional gain, that is in terms of the theta and the phi, that is PD divided by P average. Always remember, directive gain in terms is given PD divided by P average. So what is that PD? Again the 1 by 2 of E theta 5. Okay, why we are taking with respect to the theta and the phi, that is nothing but radius. Already we are taking in the previous slide, that is in the spherical form. So PD is nothing but the directive power. uh, Directive power is nothing but 1 by 2 mod of E square. 1 by 2 mod of E square. So E may be with respect to the R, theta and the phi, that's why we are taking here mod of E square. So, okay, so here divided by eta is nothing but the formula related to the PD. What is the PD? PD is nothing. PD is equals to directive power is equals to 1 by 2 mod of E square divided by eta 0. 1 by 2 mod of E square by eta 0. And what is the P average? That is the P radiated divided by 4 pi r square. P radiated divided by 4 pi r square. So at a free space, we know very well the intrinsic impedance is nothing but 120 pi, and the distance radiated is given in the numerical 10 kilometers. So 10 into 10 to the power 3 is in meters. So substitute the value of GD, which you have calculated 1.64 64, you have 1 by 2, and what is the E in terms of the theta and the phi, you need to calculate. What is the eta? 120 pi. What is the P radiated? That you have calculated in previous slide, 215.28 milli. So 10 to the power minus 3, and the 4 pi r square, 4 and the pi, then r is the 10k again, so 10k square. So in this way, mod of E theta 5, you will get 211.9 into 10 to the power minus 9. 10 raised to power minus 9. So you can convert that mod of square, take without mod, that is E theta 5 is nothing but 460.326, 460.326 microvolt per meter, microvolt per meter. So in this way, we have simplified here the three numericals, lengthy numericals, the A, B, and the C part we have simplified, which were related to your the what we can say the radiated power, which were related to your the directive gain, which were related to your the radiated resistance, which were related to your the electric field intensity as well as the magnetic field intensity. So in such a way, we have tried to simplified the numerical on the basis of your the electromagnetic radiations, and the example we have taken on the basis of your the transmitting and the receiving antenna. Thank you so much.